In this session, let's look at the concept of instruction pipeline. So first off, we're going to look at the processor instruction sequence. Then we're going to look at instructions per clock explained, so how that works. Then pipeline, and we'll go into more detail on pipelining. We'll look at some of the hazards of pipelining. There's a couple of them. And microoperations and register renaming. And then lastly, we'll take a look at conditional branches and how that affects processor execution. First off, though, the processor instruction sequence. So a single processor instruction is a sequence of essentially 4 steps. So the first step is a fetch, where the control unit accesses the memory of the next instruction, loads the instruction opcode into the internal instruction register. The next step then is the decode, where the control unit determines the actions to be taken. Now this may involve the arithmetic logic unit, the ALU, and it may require read and write access to the register or to other memory locations. The third step in the sequence then is the execute, where we actually perform, for example, the arithmetic calculation, perhaps, with the arithmetic logic unit, the ALU. So we go fetch, decode, execute, and then the last one is the write back. So this writes the results of the execution to a register or to memory, and then it updates the program counter to point at what will be the next sequence that needs to be executed. So it performs a sequence basically from the time you turn your computer on until the time that your computer is turned off. And this is what it looks like diagrammatically if we're talking about just a classic 4-stage processing cycle. So if the processor completes each step in sequence, one of each of these 4 steps, so the fetch, decode, execute, and write back, then it will do 1 clock cycle per step. So essentially then, to perform the full sequence of 4 steps would require 4 clock cycles. So we can measure how efficient a processor is by using instructions per clock metric, or the IPC, and it provides a metric on your actual processor speed in terms of how many cycles it takes to execute, to go through the full 4 steps. So the processor in the previous slide would have an IPC of 0.25. In other words, it would require 4 steps to accomplish 1 task, essentially. So it requires 4 cycles per instruction. Now, can this be improved upon? And of course, the logical short answer would be yes, it can be. But then the next question would be, well, how, right? So the main issue here is that we have circuitry that's available, but it's sitting there idle 75% of the time. And we can look at that diagrammatically, or we saw that diagrammatically, right? So it can be significantly improved upon. And we can do that through a process called pipelining. So here's a modified representation of the diagram we saw in the previous slides, where we're making much more efficient use of the resources that are available to us for using this particular scheme. So we're turning the processor into more of an assembly line, right? Like if you're at a manufacturing plant and you're manufacturing cars, for example, you're not going to manufacture 1 car from start to end before you start the next car. Along that assembly line, you're going to have the cars in various stages of assembly, right, until we get to the end where they're completed. So we want to optimize the resources that are available to most efficiently produce cars, or in this case, to execute instructions. So and this process then is called pipelining. So we fetch the next instruction immediately as the previous instruction moves into a decode phase. So we can see here diagrammatically that as soon as we move on here with the fetch to the decode, so this is our first fetch, we can immediately do another fetch. And then, so it's going in kind of an angle here. So that when the decode is passed on to the execute, then we can start the execute phase. So here we can see basically in 3 cycles, essentially clock cycles, we have 3 fetches. So we've significantly improved upon the efficiency of our processor by using this pipelining model. So what this does is it improves our IPC, which previously was 0.25. It improves it to 1.0. So essentially, using this pipelining model, we're taking advantage of our processor in a way that is 4 times faster. So that's a big improvement. That's not the only improvement we can make, though. We can also make additional improvements by, for example, subdividing to make productive use of processor subsystems that also may be idle. So we can do branching instructions, for example, where we manipulate the program counter to set the address of the next executing instruction. Also integer instructions. So we're accessing the integer portion of the ALU. So we're breaking it down into even smaller components of the ALU, as an example. Also floating point instructions. So if the processor provides hardware support, it may be separate from the ALU. So we can even decide on different types of calculations, right? And those can be done by separate parts of the arithmetic logic unit. So if we have the ability to break these down, we can again more efficiently assign resources to make sure that we can perform the instructions more efficiently. As an example for floating point, it may be possible to run in parallel, again, with other ALU instructions. And that's the point that I'm making here, the main point. So many modern processors contain multiple copies of these subsystems, such as integer ALUs. So you see here that, for example, that if our processor has the capability to, we can even run more than one fetch per cycle. So here you can see we're running 2 fetches per cycle, right? We're also running 2 decodes per cycle. And again, 2 executes per cycle and 2 write-backs per cycle. So you can see here that if we have basically the hardware available to us, we can even more efficiently take advantage of the processor resources that are available. So to support execution of multiple instructions in parallel, this is actually referred to as a superscalar processor. So this example here is an example, a diagrammatic representation of a superscalar processor that can use subsystems to perform particular parts of the execution, the 4 steps of the instruction model in parallel. So with super pipelining, it is inefficient to limit system execution speed based on what we call the worst case timing of a single instruction. So how do we handle that then? If we want to kind of avoid this worst case, we can look for cases to break a complex execution into smaller sequential steps. Okay, so what we would say providing a higher level of granularity to an instruction to more efficiently process it. Maybe, perhaps, we can break that down and perform some of that in parallel. That would be the ideal, right? And so we then pipeline those, again, called super pipelining. Now, RISC processors, by design, support effective pipelining. So reduced instruction sets are generally have already broken things down into a very simple execution phase for each piece that needs to be executed. Complex instruction set computers, though, benefit greatly from longer pipelines that break up their more complex instruction sets. So again, what we're doing is we're trying to get away from that worst case scenario where one instruction takes a large amount of time to execute and we're held up by that. So what are some hazards with pipelining? Well, it's not as simple as we've seen so far. In an example, we may have dependencies, right? Where we have an instruction that's waiting for a previous instruction to execute because it's reliant on the output of what that instruction might be. Okay, so if we have a dependent variable case, then we can't execute the next instruction until that dependent instruction has completed. So that is one of the hazards. Also, if the next phase is dependent and cannot process until the operation from the previous step is complete. And that's basically just reiterating what I just said. And so we would call this a pipeline hazard. So it's a hazard of the fact that we can't optimize with an algorithm if we have this dependency. So what can we do about it? That's the question, of course, that we want to be able to answer. We can do what's called a bypass. So a bypass is where we skip writing to the processor register, and it may be that we can come back to it and we can perform something else while we're waiting. And this is used extensively in modern processors. So we have ways of trying to optimize even if we're waiting to perform other instructions that may be waiting and ready to go. So as an example, we have two instruction sequences here. So this first instruction here, if we can't do a bypass, we might have what's called a pipeline bubble. And bubbles are bad for performance, of course, because we're sitting waiting and we're not executing. It's just like any assembly line. If there's a holdup somewhere on it, then we're not, building cars, as an example. We're waiting for that problem basically to be solved or fixed before we can move everything else along that follows behind it. So we can do what's called out of order instructions that may help to avoid these. So in these two particular examples here, this third instruction does not depend on the second instruction. So if we're waiting for this instruction to execute, but it has not yet completed, what we can do then is we can move this bottom instruction up in the sequence and do that processing before this add instruction is completed. And you can see here, so we do this out of order instruction where we can do something, right, while we're waiting, essentially. So rather than having idle hands, we can do an out of order instruction that allows us to do this processing while we're waiting for this add instruction to complete. Okay, so this helps to mitigate a pipeline bubble. Now, it may be that we might even do this and still be waiting, but at least we're moving towards better optimization of our processing. Now, micro operations and register renaming. So a micro operation, a mu op. So it looks like a U here, but this is actually the mu character. So a mu op is a substep of a processor instruction. So it's a smaller set of operations on a basic instruction. And this provides a finer level of granularity for parallelism. So we can take an instruction that may take a while to execute. We can break it down into two micro operations, and we can perhaps do those in parallel or assign them to separate resources that can execute them more quickly in a clock cycle rather than over multiple clock cycles, more than one clock cycle. So combined with additional internal registers allows for an increase again in parallelism, which is ultimately what we're looking for here, where we can get more instructions done in less clock cycles. So the use of these additional internal registers is referred to as register renaming. And this entire process of breaking down into micro operations and register renaming is called data flow processing. So data flow processing allows for parallel operations in what we call a superscalar architecture. Lastly, conditional branches. So the second key hazard here is this idea of conditional branching, where a condition makes us go to a separate set of instructions. So the next address cannot be executed until that branch condition has been evaluated. So whether it be true or false, we don't know which instruction to execute until we get the result of that condition, right? So we have some sort of a comparison. If it's this, if it's true, do this. If it's false, if it's not true, then we do that, right? So what do we do about this? So we want to avoid branching. So the idea here is to minimize conditional code as much as is possible, because this will slow down processor optimization. We could also do nothing, but then a bubble exists, right? So we can also then perform the computation of the branch condition early, so therefore not having as much of a backup or a hold up while we're waiting for that condition to be determined, whether it be, again, of course, true or false. And then the other thing we can do is guess the result. And if we have seen this kind of conditional previously, we can use algorithms that then give us a much better probability of choosing the right result. And if we can guess the result correctly more than not, then that's very advantageous. And then the last thing we can do is process both results simultaneously. So rather than waiting, it might be better just to process both simultaneously. And then once we know the result of that, then we can just drop the incorrect one. So we're processing in parallel. And then when we know the result of the conditional, we drop whichever of those two is not the correct instruction to execute based on the result of that condition. Okay, so there are different ways we can optimize our processor clock cycles again based on conditional branches. All right, so that's all I wanted to talk about in this session. So we looked at processor instruction sequence. So fetch, decode, execute, and write back. Those are the four phases or the four steps in sequence. We looked at IPC explained, and there are ways we can improve IPC like we saw. So if we just go one step in the sequence per clock cycle, then we're at an IPC of 0.25. If we can pipeline, then we can perhaps execute instructions at an IPC of 1 or more. We looked at pipelining, so the idea of taking advantage of each of the steps in the instruction sequence so that we're not sitting idle. We looked at some of the hazards of pipelining. For example, a bubble, right? Where we have to wait for a process or an instruction to execute before we can move on to the next. We looked at micro operations and register renaming. Then lastly, we looked at the issues with conditional branches and how those issues can be solved. Make less conditionals as an example. All right, so thanks for tuning into this session, and I will see you in the next.